Imagine a computer so powerful, it could solve problems beyond the reach of today's machines, all thanks to the strange and fascinating world of quantum physics. But here's the kicker. What if this revolutionary technology could be harnessed using something as ordinary as a diamond? That's exactly what Quantum Brilliance is doing, and it's turning heads in the world of computing. But here's where it gets controversial. Can diamonds truly unlock the potential of quantum computing at room temperature? Or is this just a glittering promise? We sat down with Andreas Sawicki, Technology Innovation Manager at Quantum Brilliance, to explore this groundbreaking approach. The company has recently installed its Quantum Development Kit, QDK, at the Oak Ridge Leadership Computing Facility, OLCF, marking the facility's first on-site quantum computer cluster. This isn't just any quantum computer. It's a hybrid full-stack platform that integrates quantum processing units, QPUs, with GPUs and CPUs, enabling parallel and hybrid quantum classical workflows. And this is the part most people miss. Each QPU contains 2 qubits, making it the world's first cluster of parallelized QPUs integrated into a high-performance computing, HPC environment. But why diamonds? Sawicki explains that Quantum Brilliance's QPUs rely on nitrogen vacancy, NV centers in diamond, atomic scale defects where a nitrogen atom sits next to a vacant lattice site. These NV centers host nuclear spins that act as qubits, the building blocks of quantum information. By manipulating these qubits with laser light and microwave pulses, the system can execute complex quantum algorithms. The real game changer? Unlike most quantum computers that require cryogenic cooling, Quantum Brilliance's diamond-based QPUs operate at room temperature, making them more accessible and scalable. Is this too good to be true? Sawicki addresses the skepticism head-on. Diamonds, he explains, are incredibly hard and can be manufactured to be extremely pure, virtually eliminating thermal vibrations and electromagnetic noise that typically disrupt qubit coherence. This intrinsic stability allows their QPUs to function without the need for expensive and complex cryogenic systems, dramatically reducing size, weight, and power consumption. This makes their platform ideal for real-world applications, from data centers to satellites. Quantum Brilliance's approach stands out in the industry. While many companies focus on demonstrating quantum advantage in isolation, Quantum Brilliance aims to build QPUs that outperform classical systems in terms of size, weight, and power. Their long-term vision, a compact, rugged QPU small enough to fit in a lunchbox, bringing quantum computing to everyday environments. At ORNL, they're exploring how clusters of QPUs can scale like classical accelerators, potentially outperforming GPU clusters in specific tasks. The system at OLCF is aptly named Quo, a playful nod to the Australian marsupial and Quantum Brilliance's roots. But it's more than just a name. It symbolizes a novel architectural approach where multiple QPUs collaborate within HPC systems to explore scalable quantum acceleration. With operations in Australia, Germany, and partnerships across North America, Europe, and the Asia-Pacific, Quantum Brilliance is on a mission to make quantum technology ubiquitous. But here's the question we leave you with. Can Quantum Brilliance's diamond-based approach truly democratize quantum computing? Or are there hidden challenges that could derail this ambitious vision? Let us know your thoughts in the comments below. To dive deeper into this technology, check out the companion article on Quantum Brilliance's pioneering work at ORNL.